All right, so yes, we didn't get to this one yesterday, did we? Okay. So this one, guys, there are several different ways of approaching this one. Okay. And I want to do a couple different approaches to show you that on a test or quiz, or even if you're just working with somebody else, that the approach that they're using, because it makes sense to them, doesn't necessarily have to be the approach that you use, because it might not make sense to you. Does that make sense? Okay, so some people are comfortable with pulling things apart, putting things together, using identities, using the kind of the explicit algebra that is there, and the implicit algebra. Other people are just more comfortable just using algebra. Okay, I think it's best to kind of develop a proficiency with both your algebra and your identities, because then that's going to allow you to be the most efficient with these problems. So let's take this one and just kind of show how we can work with both sides in one of these types of problems to arrive at a verifying or verification of a proof. Okay, so I want to start with the left-hand side. Actually, in this one, just to make things a little bit simpler to know what to do with the left-hand side, let's actually start with the right-hand side first. And again, that's a choice. It doesn't matter. But starting with the right-hand side, I think right now is useful. Because I look at that right-hand side, and I see a substitution right away. Okay? Now, you've got two options, and both of them will work. Okay? But to address the route that I want to take with this, we're going to choose one of those options. Okay? And we'll specify which one I want to take. Obviously, tangent squared could be rewritten as sine squared over cosine squared, right? That is an option that I'm going to kind of put on the back burner, and we're going to do that later. Okay? I see that tangent squared is there, and it's also in the same fraction as secant minus 1. Okay? Now, that jumps off the page to me, okay? Because we have a trigonometric identity, a Pythagorean identity, that says, let's write it down here, it says tangent squared x plus 1 is equal to secant squared x. Okay? That's in that blue box at the top of this PDF, right? Or this document. And it's on that handout that I emailed to you. Okay? That is one of our three Pythagorean identities. Why would I use that? Why do I think that one's useful here? If I'm going to replace, let's take that tangent squared theta over secant theta minus 1. If I replace the tangent squared using this identity, doesn't it have to replace with secant squared theta minus 1? And the denominator is secant theta minus 1. Do you see how that made a really nice relationship between the numerator and the denominator? Now, they're not identical, right? I can't just wipe them out because one's got a secant squared and the other one's secant to the first. But that numerator, remember what secant is. Secant's just a number, right? Okay? And because theta's unknown, that expression is kind of like a variable. It's kind of like x squared or theta squared or whatever. Does that make sense? It's something squared minus 1. Well, something squared is a perfect square, right? 1 is a perfect square, isn't it? Isn't that numerator a difference of perfect squares? Okay, so that's why I think making that substitution initially is pretty important, because now I can rewrite the numerator as secant theta minus 1 times secant theta plus 1. All over then secant theta minus 1. Does that make sense? Are those going to wipe out now? Okay, and remember why that happens, because this is a huge thing that people mess up all the time. If I have A times B times C in the numerator, and I have A in the denominator, the A's cancel out, right? It's a factor divided by itself, which is essentially, that's just a factor of 1, right? Okay, because I can rewrite that as A over A times B times C. If I put those over 1 and multiply that out, that still gives me back to this, right? The number one error I'm seeing, and it obviously doesn't show up in this problem, I'm seeing a lot of people do this. They're saying that they've got like A over 1 minus 1 over A, and they're wiping those out and saying they get like 1 or negative 1 or 0. Can you do that? No. Okay, that'd be like saying 2 over 1 minus 1/2, which we know is going to give us 3/2, right? It'd be like saying that that's actually 1 or negative 1 or 0. Well, 3/2 does not equal any of those numbers, right? Okay. So if you ever get stuck with your algebra with these things, because I agree that secant theta is kind of an abstract thing, okay? Understand, though, it's just a number. Substitute a number in, see what you're left with, and say, okay, can I do this algebra if I was just working with my integers or just working with my rational numbers or something like that, okay? And then realize, well, yes, I can, or no, I can't, and then say, okay, well, secant is no different than those numbers, okay, because it's just a real number, okay? I think that's a benefit for you if you can make that connection. So that's just going to leave me with secant theta plus 1, right? Secant theta plus 1. Okay. Now in the last class we stopped there. I don't know if going any further is going to be of a benefit. But if I go like 1 over cosine theta plus, cosine theta over cosine theta, right? I can rewrite that as 1 plus cosine theta over cosine theta. And what just happened? Yeah, I turned it into the left-hand side. So my goal here initially was to just work with one side and dwindle it down a little bit and maybe not see a relationship, and then grab the other side and work with the other side, dwindle it down a little bit, and hopefully then make a connection that way, right? If I go one step further here, I do generate what I was looking for, okay? So I've proven it. Does that make sense? Let's backtrack. Let's say that we did not do that, because I think seeing these various methods is very appropriate. Let's say I dwindle this right-hand side down to that, and I don't know what to do from there. So I grab the left-hand side. And it's 1 plus cosine theta over cosine theta. And there's a couple different things I could do here. I think the most obvious is to realize that 1 plus cosine theta over cosine theta it's basically you have come up with a common denominator of cosine theta out of two fractions, right? Those two fractions that blue fraction came from would have been this right here. 1 over cosine theta plus cosine theta over cosine theta, right? Does that make sense? Okay, I can separate. Usually, so this idea is like if I had 2 plus 3 over 3, that probably came from, or not probably, but did come from 2/3 plus 3/3, right? We usually go from this to that, okay, but it's a two-way street. You can go from this and separate it back to the individual fraction, okay? So why would I do that? What's 1 over cosine? Secant. And cosine over cosine is 1. And what do we notice? Those are the same. So we've manipulated the left-hand side so that it shows up to equate to the manipulated version of the right-hand side. Okay? So that is 100% as good of a proof as that first one when we just messed with the right-hand side. Okay? Let's do this. Let's say that maybe I was uncertain about separating these as fractions. Let's see if this will work. If I go 1 plus cosine theta over cosine theta and multiply by then 1 minus cosine theta over 1 minus cosine theta. When I do that, this is conjugates, right? So it gives me 1 minus cosine squared theta over cosine times 1 minus cosine. 1 minus cosine squared, is that sine squared? Over cosine theta 1 minus cosine theta. Okay. This is something that you don't usually do, but I think it's going to pan out for us. If I go sine squared theta over cosine theta minus cosine squared theta, if I multiply that out, right? I can't separate. This isn't going to be. What if we do this? What if we do this? Okay. I don't think anything that we're going to do here is going to be real obvious. So let's kind of backtrack and say, multiplying by a conjugate, maybe not the best approach here. And there's some things that we can do here maybe that are going to be useful, but I don't think anybody's going to use that approach. So let's backtrack and let's go to the route of, I'm just going to wipe all this away. Let's start with the right-hand side. And let's say, so the right-hand side is equal to tangent squared theta over secant theta minus 1. You're going to see as we work with this one, a lot of the stuff that I just erased is going to show up. It's just going to show up in a different route, okay, different order. It's going to be reversed essentially. But if I didn't know what to do, if I could not make the substitution that tangent squared was equal to secant squared minus 1, my last resort is to change everything into what? Sine and cosine, right? So let's do that. Let's take this and rewrite it as sine squared theta over cosine squared theta divided by 1 divided by cosine of theta minus 1. Is everybody okay with that? Okay, so now here's the thing. This is a compound fraction, right? Okay. It's probably a little bit more appropriate to maybe call it a complex fraction because of the fact that it's not only is it fractions inside fractions, but we've got that there. And it's the difference of fractions inside a fraction. So what we want to do when we have fractions like this, guys, is just focus on the numerator and condense that to one fraction. And that's already done, right? Then focus on the denominator and do the same thing in the denominator. So that one's already done. But the denominator, what do I need to make that one fraction? Common denominator. What's the common denominator going to be? Cosine, right? So I have cosine theta there and cosine theta there that I got to multiply by, right? So what that's going to give me, if I rewrite this as one common denominator of cosine theta, it would be 1 minus this cosine theta, right? 1 minus cosine theta. Okay. That's one fraction now, right? So the black fraction divided by the red fraction. How do I go about taking a fraction divided by a fraction? Multiply by the reciprocal. Okay. So multiply by the reciprocal, what's going to happen with this cosine here? It's going to cancel with one of these down here, right? So now I get sine squared theta over cosine times 1 minus cosine, right? Okay. Now that's kind of the same spot that we ended up in the last one, right? Okay, erased. Think about where we're trying to go with this. We're trying to go, we took the right-hand side, we're trying to get to what looked like 1 plus cosine over cosine, right? So what thing needs to go away? If I've got sine squared theta over cosine theta times 1 minus cosine theta, which of those, to get to looking like 1 plus cosine theta over cosine theta, which one of those is out of place? Sine squared, right? So let's try to eliminate that, because if I can eliminate that using a substitution, maybe that substitution will fix all the other issues that are going on there that makes that thing not look like the left-hand side. So, what is a substitution for sine squared? 1 minus cosine squared theta over cosine theta times 1 minus cosine theta, right? What is this numerator? Difference of perfect squares. 1 minus cosine theta, 1 plus cosine theta, over cosine theta times 1 minus cosine theta. What's going to happen? That cancels with that, and you're left with 1 plus cosine theta all over cosine theta. Which is the left-hand side. Okay? So all those approaches, guys, hopefully you saw maybe situations that make sense to you, you're comfortable with. I think going that route, I'm actually more comfortable with that route than I am with my substitutions initially, mainly because I'm more confident in my algebra. Okay? But like I said, I think it's important for you to develop a proficiency not only in your algebra, but in your identities as well, because that's going to allow you to be efficient. It's going to let you expedite the process a little bit. And I would agree, because a lot of you are probably thinking this, that the algebra sometimes can be confusing because it's not, they're kind of implied values, right? Secant of theta is an implied real number. Okay, I don't know what theta is, so I don't know what that number is. And that gets kind of abstract and vague for some people on what the algebra is, how the algebra is supposed to be conducted. But developing that proficiency in both identities and algebra are of benefit, I think. Okay. So on a test or quiz, guys, obviously I give, if I were to give this problem, okay, in my key, I'm going to have like 3 or 4 different routes that I could kind of grade you off of, right? With questions like that on a test or a quiz, I think it's beneficial to you to provide as much information as possible, right? If I see somebody just say, like, left-hand side equals 1 plus cosine theta over cosine theta, and then they end up going, well, that's secant theta plus 1 equals right-hand side. Should I give points for that? No. It's true, because that's eventually what we get to, but that's about as dumb as saying left-hand side equals right-hand side. I'm done. Okay, you haven't shown me the logic yet, right? Okay, so the more detailed you are, the safer it is for you in garnering points. Okay, I've got a couple others here that pulled out of the textbook that I want to cover today. The first one is this. All right, so this is just another one where we're proving our identity. Okay, so as the other ones we've done so far, we're going to first initially think about what side probably looks more complex to us, and we're going to pick that side off. Okay, which side do you think is more complex here? Left-hand side. So I'll give you a minute to write that down. and we'll pick that left-hand side off. One of my biggest things, especially writing on this board, being confined to a certain area, I'm not all that organized, and I apologize for that. Try to maintain some type of organization in your notes and on your tests and quizzes, so that, again, it is easier for me to grade, and I don't make mistakes grading it because I can't follow your work. Does that make sense? I think it's always a good idea to kind of draw, obviously your equal signs are going to tell me how to progress through there. But if you're going to run out of room and then you need to go somewhere else on the paper to show me where you're picking up with your work, draw arrows somehow to direct my attention to the flow of your work. Otherwise, I'm going to have to guess, and a lot of times I'm not very good at guessing. All right, so we're going to take the left-hand side. Which is secant x plus cosecant x all over tangent x come on. Tangent x plus cotangent x. Oh. Cotangent x. All right, so what do you think the best thing to do here in this problem is? First, change everything to sine and cosine, right? So secant becomes 1 over cosine. Cosecant becomes 1 over sine. In the denominator, tangent becomes sine over cosine. And cotangent, cosine over sine. Okay. Now, some people will argue, well, you said that when you do these, like step to step, they should get simpler, right? That's kind of contrary within the first 2 or 3 steps. First 2 or 3 steps, it's probably going to get uglier. Okay, because then it gets uglier so that we can actually do the algebra, right? And once we start with the algebra, then things are going to start simplifying and getting simpler, okay, and getting nicer to look at. So, obviously, this looks a little bit more complex than what we started with, but it allows us to look at this fraction here and now merge that, right? Okay, merge it into one fraction because it's still, right there, it's still 2 fractions right there, right? Okay, but it's going to allow us to merge them, okay? So when we merge them, what do I need to get that top algebra to be conducted? To do that addition, I need a common denominator. What's your common denominator going to be? Sine x, cosine x, right? So I want to be deliberate here. I'm going to just rewrite that fraction right there is going to be this red one here. Okay, and then I'm going to add, and then this one's going to be my second one. So sine x, cosine x. So I'm always real deliberate with my steps. I'm not going to try to come up with a common denominator and add the numerator at the same time. Does that make sense? Because I think I'm going to make mistakes doing that. And just knowing my experience with these, a lot of people make mistakes doing that. So I just rewrite that fraction there, and that fraction is going to be rewritten there. Okay? So what do I need to multiply this fraction by here? Sine x over sine x, right? Okay, so that's going to turn my numerator here to be sine x. What do I need to multiply this fraction by? So that gives me this one's denominator. Cosine x over cosine x. So I do that, and now can I actually go through and now do the algebra with those numerators? Write my one common denominator, and now do the algebra, sine plus cosine, right? And now what we've done, ultimately, is we've taken one component of the left-hand side, which was the numerator, but it was two fractions, and we've now condensed it to sine x plus cosine x over sine x cosine x, which is now just one fraction. Does that make sense? Now I want to approach the bottom the same way. Okay? So approaching this bottom here, okay, what do I need to add those two fractions together? Common denominator. What's that common denominator going to be? Sine x cosine x. So that'll be the first fraction. This will be the second one. What do I need to multiply this one by? Sine x over sine x. So, doing that gives me what up top? Sine squared x. That's a nice thing to happen. Okay, because when we're working here, nothing really generated to give me a substitution, right? Sine squared just happened. That's going to give me a substitution somehow. Let's kind of look at this one now. What do I need to multiply that one by? Cosine x over cosine x. So now I get cosine squared x. So that's even better, coupled with the sine squared. Okay. What is that going to turn into? 1. Okay. So I'm going to, yeah.
If you, like, while you're doing the work, if you forget to write in the x's every single time and you finish out that wrong, but, like, you put them back in, like, sometimes when I'm writing, like, the big ones, like the sine x, that huge fraction, I don't put the x's in because it's too much.
Okay. Let's talk about that in a minute when we're done. So when we make this substitution of that blue thing being 1, I now have at the end sine x, cosine x in the denominator, right? Okay. How do I deal with fractions divided by fractions? Multiply by reciprocals. Now, there's a shortcut here. We could just wipe those out, right? But the reason for wiping those, because they're the same, the reason for doing that is multiplying by reciprocals. Because when I do multiply by the reciprocal here, that one wipes with that one, right? And what are you left with? Sine x plus cosine x, which is indeed your right-hand side. Okay? So, the question asked was, if I'm going through and writing stuff like sine, cosine, plus cosine, sine, cosine, and you're forgetting to put the x's on there, right? Okay? And I know exactly what you're talking about because I do that all the time. It's a pain in the butt to put them in, especially if there's parentheses. If you're a person that does it with parentheses, it's just more stuff to write. No, I'm not going to, like, reading through your work, I'm not going to mark things off because of that. But what I do want to make sure that you understand is that there could be situations like that right there. If I go sine, cosine, there could be the argument that that's what you're meaning. And obviously you would have to have some variable there. Does that kind of make sense? You could be nesting trig functions inside trig functions if you're not putting the x on there. Also, when we get further into identities, the x is going to start changing to 2x, to 3x, and that's going to be a vital component to the problems. So I know, I agree, I tend to do the same thing when I'm working on my own with these, in my homework and scratch work and stuff like that. I forget to put x's on it. That's okay, as long as we understand the purpose of the x and how the structure all kind of ties in, and that when I'm done, it comes back into my answer. I would just be, for the things that we do later on, very cautious of that procedure. But no, I'm not going to. Unless it creates an incorrect answer for you, I'm not going to address it. Does that make sense? Okay. Let's do this one, okay? And we'll stop with this. This will be the last one we do. I told you last, so this is the one we simplify. There's no equation. I think the ones that you simplify are harder than the identity proofs. For the mere fact that I don't know what I'm supposed to get to here, right? And the other one, I knew once I got to sine x plus cosine x, I was done. And if I'm not there yet, I just keep going. This would be like getting in my car and start driving and not having a plan on where I'm driving to, right? Am I going to get to Cleveland if I get in my car and start driving? I don't know, okay? But if I've got an equation, I know where my destination is, right? So how can I figure out where my destination is before I even start doing this problem? Graph it, okay? Now, is it every time that I do one of these, am I going to get like sine x back or cosine? I might get something just ridiculous. I don't know what the graph looks like. But I might occasionally, it's worth a shot to see, maybe I get something back that I'm familiar with. So let's just take a moment real quick. I'll just open up Desmos here. I wonder if Desmos does this. Well, all right. Thought I could cut and paste it. So we go 1 minus cosine x divided by sine x plus sine x divided by 1 minus cosine x. Okay. What's that look like? That looks like the cosecant. Okay. It looks like the reciprocal of the sine. If I put the sine in, there's my sine. But we know that the sine and the cosecant should share maximums and minimums, right? So what's it look like I need to do that blue one? I need to stretch that blue one, right? Okay, so I think what we're going to find out here, if I look at that value right there, that maximum is a 2, right? Or I guess it would be a minimum for the cosecant. But that's a 2. Okay. So 2 sine x there. So I'm looking at, you said cosecant, but the cosecant is this, right? But if I amplify it by 2, does it give me what I'm needing? Yeah. Okay, so even though I don't, and you maybe don't have to go all that far with that stuff, as far as we did with that example, but you have technology that you can hopefully maybe gain a little bit of an idea of where you're supposed to take this. Okay? Now, it's a question in which there are no substitutions right off the bat, right? No substitutions to be made right off the bat. So we then look at the implied algebra. Okay? Order of operations is what we use when we evaluate, right? Please excuse my dear Aunt Sally, right? Can't do multiplication division here because I don't know what those things are that I'm dividing, correct? Okay, they're unknown. So I can't do that division or multiplication, so it gets me to the addition. I'm going to add these two things together. All right, so if I'm going to add these two fractions together, what do I have to have? Common denominator. What's that common denominator going to be? Okay, sine x times 1 minus cosine x, right? So this fraction here, I'm going to rewrite there. Second fraction, I'm going to rewrite here. And this is just me being deliberate. Okay, I just want to put as many steps in here as I can so I don't get lost. But what do I need to multiply this fraction by here on the left so that I get that common denominator? 1 minus cosine x, right? So I multiply top and bottom by that, I'm going to get 1 minus cosine x. It's squared, right? I'm a person that I like to do this right now. I'm going to square that, so I'm going to have to FOIL that, right? Okay, so 1 times 1 is 1. Negative cosine x times 1 times negative cosine x times 1 gives me negative 2 cosine x. And then negative cosine x times negative cosine x gives me cosine squared. Okay, so that's kind of an ugly part of this question, but nonetheless, we had to multiply that out at some point. What do I have to do over here? What do I have to multiply this one by? Sine x. So sine x times sine x. It's going to give me sine squared x, right? So what's nice here is we write this all as one fraction. Something to think about with your denominators, don't multiply them out. Because eventually the hope is that things start canceling, right? If I multiply them out, I'm not going to see, I can only think about what we do in algebra with rational equations, rational fractions, rational functions. We were able to find wholes only, in asymptotes, only when things were factored in the bottom, right? So here, we're only going to be able to find things that cancel out if the bottom's factored. So leave it alone. Don't multiply that out on the bottom. But what can you do up top? Yeah, the associative property says we can group those and make them 1. So it turns into 1 minus 2 cosine x plus 1 over sine x 1 minus cosine x, right? What's that going to turn into? There's still algebra here that we can do, right? Okay, add the ones together. So 2 minus 2 cosine x over sine x 1 minus cosine x, right? Now, the nature of this numerator and the nature of that factor right there are very similar, right? How can I get this one to look like that one? Okay, take a 2 out. If I take a 2 out, do I generate that 1 minus cosine x? And now what's going to happen with those 1 minus cosine x's? Cancel. So I'm left with 2 over sine of x. Now, this is where some people get, you can go straight to cosecant there if you want to. But the reason for that isn't 2 the same as 2 times 1? Can I take 2 times 1 over sine of x? Is that still going to give me 2 over sine x? Yes. And what's 1 over sine x? Cosecant. And now we're done. Okay. My hope here, guys, is that we recognize that problem. Mostly algebra, right? Mostly algebra 1, algebra 2, a little bit of college algebra, and 2 substitutions. Okay? Sine squared plus cosine squared, a very easy substitution. 1 over sine x, a very easy substitution. Okay? Keep working on that 7-1 assignment if you have not finished it. The take-home test, work on that. Come tomorrow with questions on that so we can talk about. I'd like to talk about that test before we start getting into 7-2 tomorrow. 7-2 is going to introduce some new identities, okay, that are, they're convenient, they're useful, but they're kind of hard to remember, okay? So we'll do those tomorrow, provided that we've got time after talking about that test, okay, that practice test.